God, that's an awful noise. Oh, oh, what are you doing? Stop! Alex here again. So apparently I'm going to be working my way through the entire Trinamic SilentStepStick lineup. I have one of each model now, I think. As you know, they're getting pretty popular and there's a lot of misinformation out there, so I put a couple other videos out just to try to clear up some issues. Trinamic published some torque curves, but unfortunately they did them at 36 volts, and most people are running these at 12 or 24, and I thought that's something I could probably clear up pretty easily. So I took the day, I built myself a jig, and plotted out some numbers for you. I have some nice pretty charts and practical examples. And now that I have the setup, I can go through and do all of my other step sticks too. So I'm interested to see how everything stacks up. Special note here, this ended up being a long form video as opposed to a 5-minute data dump style video. I wanted to do it quickie, but it just got way out of control. I rolled a couple videos into one. So make sure you look below in the description for the time index and you can skip around to the sections that interest you, and don't just watch for like 15 minutes, get bored and turn it off. Now I return you to your regularly scheduled staring at my stupid face while I talk into a camera. So we'll get to that in a bit. But first I wanted to take you through the setup of the TMC2208 because there isn't a whole lot of information on how to get them working. Now for my test rig, I just use a standard ramps board and Marlin firmware. I figured that's the least common denominator of everything. So with that information, you should be able to get them working in your machine. Here we go, let me walk you through it. Trinamic has 4 basic drivers in their SilentStepStick line. The 2100 and the 2130 represent the first generation. The 2208 represents the second generation. Now there are a couple reasons that I picked this particular model. First reason is because of stealthChop 2, and the second reason is because of the slightly higher current handling capabilities. But Alex, what is stealthChop 2, I hear you ask? I just recently heard of stealthChop 1. That's a good question, imaginary question asking person. stealthChop is their silent mode, and what it does is it switches from pure voltage regulation to current regulation. Now it works pretty well under normal circumstances, but they found with the first generation that it had a hard time with the acceleration and deceleration phases. Technically the torque in silent mode is just as good as the torque in regular mode, or better under certain circumstances, but under real-world conditions with a 3D printer, that didn't turn out to be the case. And part of that was because they just used a single stage of brute force current regulation for the chip. With stealthChop 2, they improved the algorithm a little bit and they added a pre-regulator. So it's more tightly regulated, which means that it responds better to velocity changes, i.e. acceleration and jerk settings. So I really wanted to try that out and see how it works. Hopefully I can get a video up in the future comparing the stealthChop 1 and stealthChop 2 if I can get that set up and find the time. But I'm not actually obsessed with the silent mode. I'm more interested in the current handling capabilities of these chips, because as anyone who's run the first generation know, they run hot, hot, hot. And I want to run these with higher powered steppers, so I figured it would be a good idea to try these out since they can handle a little bit more current than the previous generation. And that's mostly due to the output MOSFET's RDS on. As you can see right here, the RDS on of the 2130s and the 2100s is pretty high. It's about half an ohm, whereas the 2208 chips are a lot better. Now you do lose some of the features of the TMC 2130s, which I tested in a different video, but a lot of those features I don't actually use, so I'm not that broken up about it. I'll likely be putting out a video about what I like and don't like about the Trinamic drivers, their setup, and some of the problems that I had getting them up and running smoothly in the future. So make sure you subscribe and hit the notification bell if you want to see that video when it comes out. But one interesting feature of these chips, in contrast to the 2130s, is that they do all of their error reading and configuration over serial through the UART interface, which makes for much less hardware hacking if you're running a setup with a graphical LCD and SD card, as you can see in my 2130 video. When you plug in that single serial line, it replaces your diag, your index, and your jumper pins from your board, and you can just configure all of that in your software. You can also do a lot of advanced hardware configuration and setting of the registers over USB with a serial to USB adapter. And then they have a nice cross-platform GUI that lets you set those parameters, which I'll definitely be making video on in the future, that lets you do some really interesting things with the hardware. So here's a quick how-to for anyone that's trying to get these set up initially. If you already have this set up and you're just looking for the test data, just look down in the description, click the index to skip ahead. I bought these chips from digikey.com and they come in their unassembled state. So you can check out my other videos on this if you want to see me walk through the process of putting them together, but they work a lot like the 2130s. Like those other boards, just stick the pin headers in a breadboard and solder them up from the other side. The boards that I got had a little bit of a sloppy solder mask on the top that were covering up the thermal via pins, so I carefully scraped that away with a razor blade to make good contact with the heatsink compound on the bottom of the heatsink. And then to get them out of standalone modes that you can program them with the UART wire, you have to solder one little jumper on the board with a blob of solder, and that really wasn't all that difficult. And if you've seen my other Trinamic videos, you know that I like to run these larger heat sinks on the top, and on the bottom of the chip, I run the standard smaller heat sinks that you get for the Pololu boards. And then go ahead and plug them into your main board through either your Vaterot diode protector boards or just riser boards so you can get a little bit of airflow underneath. And then run your serial wire interface to the aux2 header, which is nice if you have an LCD screen in your aux1 header. You'll have to make a little Y cable because you have to run one of the lines through a 1K resistor, but that's not really all that tough. Then go into Marlin and set up all of your Trinamic options. Now, I'm not going to walk you through that part by part because they're going to be different depending on what you're trying to achieve with your setup, but if you want to see a general overview of it, go watch my TMC2108 video, and I go a little bit more in depth into it there. The biggest difference here is that I couldn't get the hardware library to work for the serial programming port, so I just used the software through, and you can find those options in there as well. I'd considered setting up an electronic dynamometer with some software to go along with it that would automatically do a lot of the math for me and plot things out on some nice fancy little charts, but room is at a premium in my workshops, so that would be good for a permanent setup. This is something I want to be able to tear down and set up when I need it, so I just went with a Prony brake instead, and you can check Wikipedia out if you want to see what that is. It's a very simple setup. Basically, you just hook a long lever arm up to your stepper, and then you run it at various RPMs, tighten down the thumb screws until it starts to slip, and see what the maximum readout is on the scale that it's pushing down on. I also want to be able to simulate more real-world conditions where you may not have the most rigid setup, so I grabbed a couple cigar boxes and I tested them out to see what their resonant frequencies were. And then I configured it so that I could lower these thumb screws and then clamp it against my workbench for a more rigid setup, or I could go with a loosey-goosey setup, or I had optionally some vibration damping mounts for the motors, and a self-aligning elastomer coupler that would also provide a little bit of additional damping for the shaft, just so I could see how it runs with that. I was also very interested in plotting out the temperature performance of the chip at different RPMs and different loads. So I used a piece of high temperature silicon that I clipped off of an E3D hot end sock, and I'm using that to press a thermistor into the top of the heatsink, and then I'm running that into the extruder thermistor input so that I can watch it in Pronterface. It's not 100% representative of the temperature of the actual chip's die, but it gives you a good idea of the basic trends. And I wanted to be able to use this setup to test the 2130s as well in the future, so instead of messing around with soldering things at the top of the LCD header, I decided to just go ahead and break out the ICSP programming port on the bottom with a few jumper wires, and then I just blobbed hot glue all over it to make sure that they didn't short out against the bottom of the ramps board or get pulled out accidentally when I do something stupid. The motor I used in this test is going to be this beefy SOB, which is both high speed and it's high torque, since it has both a low inductance and it's rated at 84 ounce-inches of torque. It has a rated phase current of 1.7, which means that if I run it at the datasheet max of 1.2 amps RMS from the silent step sticks, I can hit 100% if I want to. Since it's a 48mm stepper motor with multiple steps, the rotor inertia is going to be fairly high, which means I should be able to exacerbate any of the negative effects of acceleration and deceleration on the silent step stick mode, so that's good as well. Since I wanted to keep this setup as 3D printer-ish as possible, I'm going to be sending all of my commands through Pronterface and standard Marlin G-code into a Ramp's Arduino setup. So that means I don't have the rotational speed settings of a standard Gerbil CNC setup. So I initially started doing the math to convert that radial speed into linear speed that I can use to directly correlate to the steps per millimeter in Marlin. But I quickly found out that that would take an eternity to calculate for all the different setups I wanted to try. So instead, I just grabbed the RPM gauge off of my coil winder, stuck a little neodymium magnet on the shaft, and took actual RPM readings at different setups just so that I could make sure that there weren't any mistakes, and it made everything go a whole lot quicker. Then it was just a matter of 3D printing a couple of tidbits that I was going to need for the test, and trying it out. And it works great, but next time I'll use a wing nut on the adjustable side to save a little bit of wear and tear on my fingertips. I don't mind suffering a bit for science, but, you know. Make sure if you're doing this that you're going to have your driver monitor status enabled, as well as a TMC debugging. And then at any point in time you can use an M122 command to get the status of your driver. You can also easily change the RMS current with an M906 command. I used the G1 linear move command, disabled any of the end stop commands in Marlin, and then set the axis I had the driver on just really long. Anyone who's worked with me knows about my crazy notebooks full of insane scribbles. This wasn't any different. But I went ahead and I put it in a pretty spreadsheet so that I can make some charts for you guys. Special note that I used the actual force exerted on my scale in this setup in the cells for the torque values. Now I use a 10-inch long lever arm, so all you have to do is take that and multiply it by 10 to get inch ounces of torque. It just looked a lot cleaner this way. The big things that I wanted to look at were the standard setup, which is 16 times microstepping with 256 times interpolation engaged in a 12-volt setup, and then compare that in both spreadCycle and stealthChop mode. I also added quarter stepping in there as opposed to 16 times stepping with the 256 times microstepping engaged. I also tested that same setup at 24 volts so that I can compare those two, as well as testing them without the 256 times microstepping interpolation engaged. And then I took a decent range up near the top end of stealthChop and I ran that at several different currents to see what the power drop would be. All the advice in these areas so far that I've seen around the internet is more or less anecdotal or extrapolated from data that wasn't tested under particular usual running conditions. So hopefully this is helpful to everybody and it'll give you a better visualization of what's actually going on in these different modes of operation and operating points. For the sake of full disclosure and accuracy, here are the operating conditions I ran these tests under. I was at 1 amp RMS motor current, which means that was 1.414 peak, and that puts it at 85% of the maximum stepper current. I tried to stay as close as possible to the stock chip and Marlin settings so that this would apply if you just plunk these into your board and don't fiddle around with the settings a whole lot. Hybrid mode was turned off so that I could completely test stealth and spreadCycle separately. I did not do any automatic driver tuning. Now these drivers will tune themselves and you can set up automatic current and voltage and all that nonsense. I wanted to make sure that this was as if some noob just plunked it into his board, so I didn't mess around with any of that. And just to make sure that it was on the level, I completely reset the board between each test run. I didn't use a cooling fan because a lot of people don't put that on their boards, except where noted, because I did run a couple temperature tests, and I'll get to that in the explanation. I used serial mode, not standalone mode, and all of the changes were done via software, either recompiling Marlin or just sending changes through Pronterface. And to make sure that these were applicable across a range, I used several different default axis steps per unit settings. And these were centered around the Prusa i3 specs because that seems to be the most popular design across the board for people that are just trying to get into 3D printing and DIY stuff. Now, as you may or may not know, StealthChop has a real hard time with burst stepping or multi-stepping or whatever you call it, double stepping, quad stepping, which Marlin will do to save clock cycles when you get up to higher speeds. I did not bother purposely with those breakpoints because I wanted to see how it would run as if somebody had no idea that worked, because there isn't a whole lot of notation on it, and just plunked these boards into their machine and said, hey, go at it. Another note real quick is that I just tested the torque. I did not test the torque at acceleration. So a lot of people are running into problems with StealthChop when they're accelerating and decelerating. I'm going to try to cover that in another test. I just wanted to get this basic stuff out of the way at first, so that way we have a general baseline overview that we can use to compare other things to. So first up, we have the 12-volt comparison. Now this is spreadCycle at 12 volts, 16 microstepping with interpolation, StealthChop 12 volts, 16 times microstepping with interpolation, and spreadCycle at 12 volt with quarter stepping and interpolation. If you've seen my videos in the past, you know that I heavily favor 24 volt and think everyone should be running higher voltage on their drivers. And as I get to the next chart, you're going to see why. But this represents the mode that most people are going to be using right off the bat. It's also what Marlin is tuned around right out of the box. So as you can see here, the yellow line represents StealthChop, and that holds pretty good torque up to 100 RPM in this setup. Then it starts to drop like a stone. That's not surprising. Anything above that is going to be better off in spreadCycle mode because you're going to get more torque out of it at the expense of a little bit of noise. And that's why hybrid mode exists, where it switches between modes. And as you know, you can change that breakpoint in Marlin depending on what works best for your particular printer. It is, however, very interesting to note that spreadCycle in quarter stepping with interpolation isn't all that much louder than regular spreadCycle at 16 times interpolation, and it has a lot more torque across the board than either mode. That also has the advantage of saving CPU cycles because you have to send fewer steps per second, so that's good news for people that either want to run faster, are running reduction gear ratios on their belts and pulleys, and people that are running a Core XY or a Delta setup where you have a lot more computational headroom that's going to eat into your possible high step rates. It's definitely something I recommend messing around with if you fall into one of those categories. Or if you were finding torque loss due to acceleration in stealth mode and you really don't care about the absolute silence, that way you can just set one mode across the board and be done with it. It's also worth mentioning here that a lot of direct drive extruders are going to run in the single digits RPM range where everything is a little bit rough. You want your motor to run as vibration free as possible in that range, so the recommendation is usually StealthChop at the highest microstepping you can do, plus interpolation engaged, because that's going to excite fewer resonances in the actual motor and setup itself, and you're going to get a lot more torque at those lower ranges and a lot less filament skipping. And that's why spreadCycle, as you can see from the blue line, is not very good down in that range. But it is worth noting also that, as we see from the green line, if you drop the microstepping down and engage software interpolation, it does pretty good down there, better than StealthChop actually, at the expense of a little bit of extra noise and vibration. But if you want to avoid all that, let's move on to the next chart, and that kind of turns things on its head a little bit. Here's where things start getting interesting when we up the voltage on our motors. I run all of my machines at higher voltages, and recently Prusa has moved up to 24 volts on the Mark III i3 machine, which I think is a great move, and you can see why here. All of a sudden we're getting much better numbers at low RPMs across the board, and we're also getting better higher speeds as well, and a more consistent torque curve across the range. Now we still do have that drop off from StealthChop, and that's, like I said, to be expected, but it's at a higher range, which means that you may be able to keep it across the board without having to worry about hybrid mode, and you could be fine. And our 16 times microstepping is as good as or better than quarter stepping across a lot of the range there. And while it does look like for consistency across the range, if you don't want to play with hybrid or stealthChop mode, you still want to go to quarter stepping with interpolation. If you're going to be needing that top end speed, it still looks like you should be running stealthChop with 116 plus interpolation up to about 250 RPM, and then switch to spreadCycle mode, 16 times microstepping with interpolation above that. But again, what's good for the Delta and Core XY guys and the reduction ratio guys is that quarter stepping looks pretty good. So that won't artificially limit your top range when you're going into double and quad stepping, since you'll be able to spit out 4 times more steps per second than you would in 16 times microstepping. For kicks and giggles, I tested this at 24 volts with 16 times microstepping and the interpolation turned off in both spreadCycle and stealthChop modes. And as you can see here, spreadCycle didn't change all that much. The curve is basically the same as it was in the last diagram. But in stealth mode, we have a much more rapid drop off of the torque at higher RPMs. I couldn't get the motor to even turn without any load at those rates because it just resonated so badly. For that reason, I also don't recommend, and I didn't bother charting out quarter stepping without interpolation engaged because it's just so rough and loud. So here's where the rubber meets the road in terms of the 12 versus 24 debate. You can see from the blue and the green lines, that's going to be your 12 volt operation. The red and the yellow lines are going to be your 24 volt operation. And without even studying this chart very closely, you can see how much benefit you get from moving to 24 volts. Not only do you have higher top speed and more consistent torque across the range, as well as higher torque at low speeds, but stealthChop behaves a little bit better and it buys you a higher crossover point if you're going to be using hybrid mode. And if you look at the red line, which is stealthChop at 24 versus the blue line, which is spreadCycle at 12, you can see that not only do you have a higher top end speed and better overall torque, but at no point in the curve is spreadCycle at 12 better than stealthChop at 24. You're just getting better overall performance. And since the torque crossover point at 24 volts between stealthChop and spreadCycle is so high, i.e. up near 300 RPM, conceivably 90% of people can probably just run stealthChop at 24 and be done with it. You might want to engage spreadCycle just for really fast or highly accelerated travel moves, but that's dependent on your setup. If you're running a Core XY or a Delta printer, I would say you definitely want to set that crossover point a little bit lower and go into spreadCycle, since your domain is going to be much more way up in the high RPMs. I plotted out here the effects of running a lower stepper current when we're way up near where stealthChop starts to get ragged, but where it's still fairly solid. So as you can see here, so as we know, stealthChop at a particular lower current rating can give you better benefit than standard chopper mode at the same current. Partially that's because of the vibrations that it doesn't excite, partially because of its smooth movement, and partially that's just because it's using current handling instead of voltage handling, but I wasn't exactly sure what the drop was going to be. In standard chopper mode with a different driver, we would expect if we cut our current down to 50%, we would have 50% the torque. Generally speaking, that doesn't translate one-to-one for printing moves because you're talking about your holding torque, and we also have to worry about our acceleration, of course, and our pull-in and pull-out torque. But as we can see here for our dynamic torque, when I cut it down from 1.2 amps or 1200 milliamps to half, which is 600 milliamps, which some people have to run because of heating problems on their boards, we're not actually getting that much of a drop in torque. It's about 75% of the torque of the other setup, so that's pretty good. And it means you don't necessarily have to be running on the bleeding edge because you don't get that big a penalty for turning down your current a little bit. But just keep in mind that the problem that a lot of people have with StealthChop mode is not the holding torque, it's going to be the torque on the accelerating and decelerating moves. And that relates much more to how the chips handle that. So I'll have to cover that in a future video because I will have to do a completely different setup for it. Make sure you subscribe and hit the notification bell if you want to be notified when I post that in the future. So here's a big confusing spaghetti chart of absolutely all of the test data laid on top of each other, which I smoothed out with some Bezier curves just to make it a little bit more readable. Now I know it's confusing because there's a lot going on and some of these colors are pretty similar, but you can see the trends of what's going on here. And this might help you select the mode for your particular usage. And it lets you see the difference between 12 and 24, different microsteppings, etc. So if the question is what single mode you should be running if you have to choose, it looks like the most consistent across the board with decent top end is going to be StealthChop with quarter stepping at 24 volts plus 256 times software interpolation. That seemed to be most consistent. It's good on the low end, it's good on the medium range, and it also has a decently fast top end speed, although your torque does start to take a nosedive up there, and that doesn't take into account acceleration and deceleration. Now, if you want to maximize your smoothness and minimize your noise, you're going to have to go to 24 volts, 16 times microstepping with interpolation engaged, and then fiddle around with your hybrid crossover point to find out what the best range is depending on your particular pulse rate. And last but not least, we have the booby prize, and that's running anything at 12 volts. If you run pure StealthChop at 12 volts, you're going to get okay-ish performance at the lower speeds, but that drops off pretty high at the top end, so you might have some problems with that, as well as with torque on acceleration and deceleration. But if you run pure spreadCycle, you have terrible performance in the lower RPMs, even though you have better high-end RPMs, but it's still not anywhere close to any of the 24-volt modes. Best you can do is use hybrid mode, find a decent crossover point where you're using StealthChop at lower speeds, and then you change to spreadCycle higher up. But you're better off switching to 24 volts and then using just about any setup. Now this note is just a friendly reminder that this chip does use StealthChop 2, not StealthChop 1. I will try to get torque curves out on the other Trinamic drivers as soon as I can. I also want to test the Allegro and the Texas Instruments drivers as well to see how well they hold up under the same conditions. So stay tuned for that. Again, subscribe, hit the notification bell. Now, I don't have any fancy graphics for this, so I'm just going to put this title up and read it off to you. But in terms of the temperature readings, these chips ran a lot cooler than the other Trinamic chips. So that's worth keeping in mind if you have a setup where they're either enclosed, or if you have a particular driver that needs a little bit more current, or you run at lower speeds more. Because these drivers are pumping out the most current at lower speeds because that's just how steppers work. So in order to test the limits, I programmed some G-code that cycle between running 1 to 5 RPM and then full holding current. And as a result, even with just ambient cooling and the 2 heat sinks on the risers, I couldn't get the chip above 100 degrees Celsius. But those heat sinks are pretty effective. Just blowing on it with my breath, I could get the temperature to drop down to 75 degrees. And when I stuck my auxiliary gooseneck cooling fan on it, which is just like a 80mm PC fan, I got the temperature to drop under 50 degrees and it was fine. Now, even though I couldn't exceed 100 degrees in the time that I cycled that test, the heat did creep up and creep up and creep up ever so slightly. And as your heat goes up, your RDS on is going to go up as well, which means your package is going to be getting even hotter. So that's just something you want to keep in mind if you're printing a longer print with low speeds. My advice, as always, is put a fan on it, even if it's just a small one. Thanks again, hope that was helpful. I'll be getting more information out soon. If you want to support this channel and what I'm doing, you'd like to see more of these videos, check out the support links in the video description. catch you in the next video, but in the meantime, go make something awesome.